presentation this month I'm going to be doing is on space weather. It's interesting. I kind of put this together as a learning project for me. You know, shamelessly kind of stole slides from a couple of different presentations that were done. And it's interesting, as I was doing this, I kind of got the impression that the sun is a great thing. It provides life and sustenance, but it's also doing its best to kill us. And you'll see the majority of presentation kind of supports that. I'm not sure I'm ever going to want to go outside there in the daytime again. And again, it's a mixture of slides from that Norwegian Space Center representative and a couple of scientists from the United States. Okay, space weather, what is it and why should we care? I mean, I think everybody here probably knows what it is and why we should care, but there are things, the sun is relatively stable, but not really. We're living next door to a live, ongoing atomic explosion, which is constantly sending things in all directions. Really, there's a couple things that are keeping us safe. The major thing is the magnetic protection that we have from our own magnetic poles. The other thing is that we're a small moving target, and the sun is just belching things out in all directions. At 93 million miles, we're a tiny little moving target, about 3 arc seconds across. We just don't get hit that often. But when we do, as you kind of see in the upcoming slides, when we get hit, it can be pretty spectacular. So what do we really mean about by space weather? Okay. There's really 4 phenomena that make up space weather. All right, the ones that we're kind of really all familiar with, there's flares, which bombard space, on the Earth sometimes with X-rays and UV rays and extended UV rays. And these are pure energy particles that travel at the speed of light. They reach the Earth in about 8 minutes. The second is proton showers, which are actual physical particles. They travel at anywhere from 20% to half the speed of light. They reach the Earth in about anywhere from 15 to 60 minutes. And these are, we'll get into more details on these later, but these cause tremendous damage, and they go through just about anything. The third one is coronal mass ejections. Again, these are physical particles that get ejected. Not quite with the intensity of the proton showers. The coronal mass ejection takes about anywhere from 1 to 3 days to reach the Earth. And the third type of space weather are radio bursts, which again is an energy phenomenon. Takes about 8 minutes. To some degree, these are blocked, at least partially, by the magnetosphere or by the actual air particles in the atmosphere, but not all. So I'm thinking them kind of one at a time. The solar flares. Solar flares tend to happen when the magnetic fields that are always present under the surface of the sun break above the surface of the sun. Many times the magnetic fields can be seen as loops that begin at one sunspot and end in another. Those tend to be the stronger ones, but they don't have to begin and end at sunspots. They can release, like it says there, they can release in seconds energy corresponding to several billion megatons of TNT. The gas that's released in those, it tends to fall back down onto the sun, but it's heated to 20 million degrees Fahrenheit. It emits enormous amounts of UV radiation and X-rays, which then travel across space. It hits the Earth just over 8 minutes later. Most of it is blocked by particles in the atmosphere, such as ozone. But some of it is not. Some of it gets down into the lower, some of it gets down into the lower orbit part of the atmosphere, and that can cause damage to the things that orbit up there. We'll see that later. Okay. This is a typical picture, and we've probably seen variations of this before, of the kind of radiation that gets blocked and the kind of radiation that makes it down to the surface. I kind of wish I brought a pointer, but as you can see, the infrared and the visible light are the two bands in the middle. Those are the normal energy bands that make it down to the surface. They're generally benign. Those are the ones we want down at the surface. The ultraviolet and the extreme ultraviolet are the one, and the X-rays are the ones that get the three bands over to the left. Those are the ones that get released during flares, and they get blocked up in the middle bands of the atmosphere. And then the charged particles, which we haven't really gotten into, those are the ones that they get released during the proton showers generally. They get blocked in different parts of the atmosphere too. One of the things that I thought was really interesting about this slide, if you look at that wavy, the larger wavy white line, that's a temperature line. And I thought it was really interesting how the temperature, you always kind of think about the temperature just going down fairly steadily as you go up further in space. The 300 degrees Kelvin that it shows at the surface corresponds to about 80 degrees Fahrenheit. So we're talking about an 80 degree Fahrenheit day. All right, and the temperature does go down as you get a little bit higher, and then it goes up a little bit again, and then it shoots up tremendously as you get up into the ionosphere and the thermosphere and the magnetosphere. And I was wondering, how can that be? You always see the movies, and the guy gets thrown out into space and he freezes. 3,000 degrees Kelvin is about, I believe, about 5,000 degrees Fahrenheit. Now, it's a little bit hard to explain how that can happen. The particles of the atmosphere up there are excited by the radiation that's always up there. Think of it, temperature equals motion. Okay? The particles that are up there are excited to the point where they measure that high a temperature. But they're also, the atmosphere up there is tenuous to the point where that temperature can never be passed on to anything else. You could if you get thrown out of a the space station or a shuttle up there, you will freeze. Assuming you don't die of asphyxiation, you will freeze. You'll freeze in the middle of 3,000 or 5,000 degree particles of extremely tenuous air. It's a little hard to get your mind around that, but that temperature scale there is kind of interesting. The typical aircraft is just below that 10-kilometer line. They fly at about 7 kilometers. A jetliner. You'll see the space station is around 450, I believe, or 500. So, and you see that during solar flares, the space station the space station gets all that radiation. So, one of the things that solar flares, I don't know if this is more detailed than anybody wants, but solar flares are classified as A, B, C, M, or X according to how much X-rays they cause in the atmosphere. Basically, it's called X-ray flux, watts per square meters, a measurement of X-rays in the atmosphere. All right, and then the chart on the right kind of gives an indication of an X2 and M5, and then within each letter there's a certain a number indication. So there's an M1, M2, M3, M4, etc. That's just the way that they classify the solar flares by how many X-rays they release or they bombard the atmosphere with. So. Now, particle showers, again, are a physical phenomenon. They travel nearly the speed of light, consist mostly of protons. They're also called proton showers. They usually take less than an hour to reach the Earth. And they do cause actual physical damage to electronic equipment. Now you see two examples up there of what they can do to a digital camera. Those are two photos taken from, I believe that's Soho. Yeah, those are Soho photos, taken very close together when a particle shower hit in between the photos. And you can see it wasn't actual damage, but you can see how it almost blinded the Soho camera in the second photo. And it severely degraded the quality of the image. And the particle showers also, or proton showers also, play havoc with the ozone layer. This was a particle shower. You can't see the exact date here, but this was a particle shower. 2000. It takes quite a while for that to repair itself. It's a much more severe effect than an X-ray, than a flare is. I'm sure to somebody that studies these things, those lines are very significant. The chart on the left shows the effects of an X-ray flare, and then the chart on the right shows the effects using the same scale of a. Actually, no, that's quite a larger scale, actually, of a proton shower. So it's really just meant to the effects that they have And they're really an early warning system. They're the thing that's up there that's called, like the second one from the top, it's called, on the slide, it's called a solar probe. It's been renamed to the Parker space probe. The what?
That was just launched.
Yeah, that's fairly recent. That's fairly recent. That's the one that is, it's touching the sun. It's right in the outer atmosphere of the sun. The thing that I thought was interesting is, Dave, part of this system is actually Voyager. If you see off to the left, Voyager 2 is providing data on how far the emissions from the sun reach. So they're using data from Voyager as part of all of this. SOHO is in there. Which ones?
Solar Dynamics.
Yeah, I'm sorry, John, I can't hear you back here.
Sorry, SDO, the Solar Dynamics Observatory. There's a web app for that.
Stereo.
Yeah.
Some of these work in pairs. There's some of them there that are triplets and four. Stereo, unfortunately, is a single now. Stereo B lost communications some years back.
Parker Solar Probe is the first observatory that's going to go around the poles of the sun. It's only expected to make 9 orbits.
Yeah, I think it just completed the third. So it's got a ways to go still. All right. And this is just a picture of the stereo craft. There's the stereo A for ahead and stereo B for behind. They're 180 degrees apart, taking stereo views of the sun in different frequencies. Like I said, unfortunately, in 2014, stereo B lost communications, and they have not been able to reestablish communications. They know it's there, but it's not communicating. And this is an example of Superstorm 2012, and photos of, you can see the prominences coming out of the sun from stereo, the types of photos that it takes in different frequencies. Luckily, I don't believe any of those were aimed at us. So, all of those satellites are fairly recent. And we know what's happening. We know the kind of things that the sun can do. We know the effects that it has on here. Using that data, scientists were able to go back and look at some of the unusual, odd electrical happenings that happened on the Earth over the last 150 years, and kind of get a clue on why they may have happened. So I thought this chart was really interesting. Okay, starting with 1847. All right, strange currents, in the telegraph line between Derby and Birmingham. Now this is England. Okay. 1859, telegraph service disrupted worldwide, probably by a geomagnetic superstorm. All right, again, some days later in 1859, largest geomagnetic storm in 500 years. 1921, a great storm, causes fires, burned out cables, disrupted telephone service. In 1989, a geomagnetic storm collapsed the Quebec power grid. And then in October 19th through November 7th, 2003, that's a long duration. That's the famous Halloween storm. Interrupted GPS, blacked out radio, caused emergency procedures in nuclear power plants, and blew out some transformers. So. Going back to 1848, telegraph lines between Pisa and Florence in Italy were knocked out. 1851, these were all, you know, in retrospect, have all been attributed to space weather. The telegraph system in New England was disrupted, and sparks and fires were reported. This I thought was fascinating. In 1859, and you can look this one up, in 1859, the telegraph system in Boston stopped working. What they did, what the telegraph operators, to get things working again, and I don't know how they came up with this, but they disconnected the telegraph system in Boston from all power, from all batteries, from all external power, and it was able to work again for 90 minutes just by the overload of electrons in the air from the geomagnetic storm. All right, so the geomagnetic storm caused such an overload of electrons in the air that it basically overloaded the telegraph system until they disconnected the internal power, and it picked up enough ambient power from the air, and they were able to get the telegraph system working for 90 minutes just from that. I have no idea how that happens, how that works, but it did. And you can look that up. It's written up. So, LORAN, long-range navigation. X-ray flares disrupt that on the day side. Proton showers affected in the daytime. Geomagnetic storms disrupted day and night globally. Normally, the normal accuracy is what is that, about 50 times worse, about 25 times worse during a geomagnetic storm. And it can actually be rendered useless for several hours. We're not even to the good stuff yet. Okay, effects on telecommunications cables. Now, you'd think that undersea cables, you'd think that underground cables would be safe, but apparently not. Okay, undersea cables from Newfoundland to Scotland were affected, with sound being distorted. All right, optical fiber is not affected, but they do have signal amplifiers that are affected. Oops, sorry. You know, and then obviously navigation, GPS navigation systems. Causes what's called scintillation, which is an actual term. The signal, like you see in the lower right-hand slide, the signal bounces back and forth. It degrades the signal. There's a phenomenon called TEC, total amount of electrons. Can introduce errors up to 100 meters. And then radio bursts can jam the signals. 100 meters doesn't sound like a lot, but it accumulates. And I'll show you that in the next slide here. All right. The map up above, you see Pennsylvania, you see Virginia, West Virginia there. These geomagnetic storms create what's called TEC walls. That gray line is a TEC wall. That wall is, I don't know, what is that, about 100 miles. The GPS signal along that wall is degraded. It's about is probably about has about a double the delay that it normally does. An airplane flying along that line accumulates. That signal accumulates. If it flies along that line, by the time it enters that wall and exits that wall, the GPS signal can be off by miles. That wall also moves. If you see the arrow, that wall moves. All right. The example above is it's 50 kilometers wide. It's a wall 50 kilometers wide, and it existed for 30 minutes, and it kept, it was moving from Pennsylvania down through Virginia the whole time. Messing up GPSs and airplanes and cars and all navigation systems along the way. And then this is the big one in 2003. Navigation system called WAS, which is a combination of GPS and satellites and other satellite systems. And if you look carefully under that blue and red and yellow, you'll see that one in 2003 basically affected the entire United States. The WAS is an augmented system that the FAA uses, and there was a 15-hour loss on, this again is the Halloween outage. There's a 15-hour loss on the 29th, 11 hours on the 30th. So, I know, I'm getting repetitive here. I'm going to skip through some of these. Okay. And again, this is just a slide that shows all the different uses of GPS and what can be affected by the loss of those systems. It isn't just communications. Rail yards, switching towers, ship routing, wireless internet, banking, ATM, energy plants, things that you wouldn't necessarily expect to have to use GPS. Obviously effects on military systems for navigation, early warning systems, search and rescue. This is an interesting slide. This is a SATCOM. This is a 1997 test. This is a private communication test that was disrupted by a geomagnetic storm. You look at the line. The quick brown fox jumps over the lazy dog's back, and look at how the communications was messed up. And for that, there's a 2-minute duration, or actually it looks like about a 1-minute duration of the signal degradation. And you can see how the signal itself was messed up, in the red, the green, the brown lines. Radio bursts. Radio bursts can mess up your cell phones. Interference can lead to dropped calls. And effects on airplanes, high-frequency communications, especially on polar transatlantic flights where the communications is already a bit spotty. The energetic particles, that's more than just communications. But anyway, GPS and navigation. The effects on polar routes. Polar routes are the chart on the bottom there only goes up through 2007, but polar routes are becoming more and more popular. They're faster, they're cheaper. There's no communications along the polar routes is more difficult already, just because of the way that the magnetic field around the Earth bends. When there's a geomagnetic storm, communications basically can become impossible, and including GPS navigation across a polar route can become impossible. This is repetitive. Disruption of power grids. This is an interesting one here. Directional drilling relies on GPS, which I didn't realize. The oil industry buys geomagnetic maps to guide the drill and to monitor the well directions. Okay, and I think this slide here kind of points that out. When you have all these wells drilling sideways, like if you have in the lower right-hand slide there, you have no idea underground where all those other wells are. They rely on GPS information to guide them. You know, sometimes within feet of other wells. Obviously effects on the compass. You know, and then we got the impacts on animals themselves. Animals have natural compasses built in. They have a mineral called magnetite in the bundles of nerve cells, which can be messed up. And then this is the famous Halloween storms. More than 20 satellites and spacecraft were affected, and that doesn't include any classified military instruments. More than half of NASA's satellites at the time were affected. The Japanese lost one. Severe radio blackouts, high frequency radio blackouts, power failures. Himalayan climbers lost their satellite phones. LORAN navigation. And the radio monitoring device on the Mars Odyssey was knocked out. Mars actually lost part of its atmosphere because of that. That was a pretty nasty one. So as we go further out into space, the effects on satellites can be pretty severe too. There's a phenomenon called surface charging. As the high energy particles, well, again, these are physical particles, hit the satellites, they can actually create an electrical charge on the surface of the satellites. It can obviously mess up the electronics in the satellite itself. It can increase the drag. Now you say, okay, how can it do that? It can increase the drag because it increases the, we'll get more into this a bit later. It increases the drag, the density of the air, tenuous as it is, that the satellite is going through. And it's a much more severe phenomenon than we realize. I'll get into that in some other slides. It causes orientation problems. Causes problems with the star trackers, degradation of solar cells. I'll get into all of that. All right. And here's a slide that shows SOHO. Let's see. Okay. I probably knew at one point what the detail was here. Anyway, this shows some damage to SOHO from high energy particles, but I'm not sure what the detail is here, so we'll skip. Okay, again here, this shows damage in SOHO solar array from a proton event between the two. Actually, every single arrow is pointing to damage. I don't know how to quantify that though. SOHO is in an unenviable position because it's right there and taking the brunt of anything that comes out of the sun. Now, orientation problems. Okay, here, just like you have a, just like you'll orient your telescope with a guide star. A lot of satellites will do the same thing. They'll use a guide star. If you see the star picture on the left, they'll orient on a star. When you have a proton shower, that picture of the guide star that the satellite is looking at, gets spattered with points of light, and it's very easy for the satellite to lose that guide star. So the orientation can get really messed up. can get easily messed up. Okay, surface charging. Again, surface charging can be a problem. High flux of electrons in the atmosphere, variations in atmospheric density, and just plain damage to satellites. You know, here's examples of satellites that have been damaged. You know, annual loss, and this is back in 97, 98, annual loss of $500 million just from satellite damage from this phenomenon. As Galaxy 15 became what's known as a zombie sat, it was disrupted in 2010. It continued to transmit, but it wouldn't accept commands. And basically it became out of control. And then there's the increased drag in the upper atmosphere. And this is, again, this is a fairly recently understood phenomenon from the UV and X-ray fluxes. Causes increased friction for satellites, which causes a faster orbital decay. And now there's pretty sure that was one of the reasons why Skylab fell down faster than predicted. The solar maximum mission. When there was a solar storm in 1989, the solar maximum mission dropped down 5 kilometers during that solar storm because of increased drag. The Hubble drops about 10 to 15 kilometers per year and has been boosted 4 out of 5 times during servicing missions. And the drops can be pretty exactly correlated to solar storms, solar flares. The one in the box there is a solar flare and the resulting loss of 7 kilometers in altitude for the space station. You know, it affects this chart. This chart tracks every satellite. You know, the one that's the dark bold line there is the Hubble space station. But the same thing affects all satellites. Makes tracking of satellites difficult, or makes predictive tracking of satellites difficult. You know, and then there's the like you would expect. We're just really starting to understand the radiation hazards, which are more severe than we realized. Certainly more severe than we realized 50 years ago when Apollo was going up. You know, polar flights themselves, you know, present a radiation hazard. Polar airline flights present some radiation hazard. You know, space shuttle, the International Space Station, you know, missions to the Moon and Mars, all hold some level of hazard, more so than we realized. Okay. Let's skip down. The ISS astronauts do wear personal dosimeters to track that. But here's an interesting slide here. The Apollo program, this chart down here correlates the numbers along the top of the slide, 7, 8, 9, 10, 11, all the way through 17, show the times of the Apollo flights. And then the small yellow reddish bars rising from the bottom show the solar proton shower events that happened during that same span of years. You'll see that what's circled there in 1972 is a proton shower that was so severe that it probably would have been fatal if it happened when either Apollo 16 or Apollo 17 astronauts were on the moon. So that's what the title of the slide says, pure luck. If it had happened a few months earlier, a few months later, we could have lost the astronauts that were on the moon because of that solar, the proton shower. You know, and then again, if there was if the space program had continued to 1989, in 1989 or 2003, there were also proton showers that contained lethal amounts of particles. Now is the mission to Mars that we all are expecting to happen sometime relatively soon. You know, radiation hazards from a 1,000-day mission to Mars and back is a huge challenge, big challenge. How do you protect astronauts on the way to and from and while on Mars? I haven't heard anybody really talk about that. You know, they talk about a lot of things, but I haven't heard anybody really discuss that. You know, like, I'm sure everybody here watched The Martian, right?
Yes.
Watney?
I own it, I actually own the movie.
Watney? He spent 560 days on Mars. Be interesting to see what his DNA looked like when he came back, because Mars has no, has no magnetic, magnetic shield. Every bit of radiation that hits Mars hits the surface. You know, that movie addressed a lot of science, but it didn't address the radiation and the flares and the proton showers and all that good stuff that he would have been bombarded with. So, how did he fare after 560 Earth days on Mars? Not to mention the trip back and forth. Again, hazards on Mars, radiation doses from solar storms and cosmic rays. Mars lacks a magnetosphere. You know, that's harmful for both humans and electronics. Modern and the weird, the funny, it's obvious. You know, the modern electronics are more effective than the old technology that's used on the moon. It's very important that we have more, better, timely space weather warnings. Communications problems with the Earth during solar flares because of ionization in the Martian atmosphere. You know, maybe one of the answers is, and that's supposed to be a little enterprise on the bottom there, could we generate an artificial magnetic shield around the spacecraft? Kind of like the Earth has. Maybe. Hopefully somebody's looking at that. I like to think somebody's thinking about that. So here's places, if you want to learn more. If you want to, there's three good sites. And actually, if you get this slide, if you get this slide presentation, those are clickable links. You can click on those links in the slideshow. One of them is a NOAA site, one of them is a NASA site, and one of them is a space weather site. That's it. Scared yet?